Welcome to the Teachers to Tech podcast. I'm your host, Dean. This is the podcast where we tell you how you can grow your tech skills, whether you're starting from scratch or just want to go farther. You might be thinking about a new job, a whole new career, or just a new hobby. We'll have something for everyone, so keep listening. Hello everyone, and welcome to Season 4 of Teachers to Tech. I'm your host, Dean, and this is episode 1 of the season. For the topic, I have chosen why and how machines talk to each other. And I'm going to explain to you a little bit about how that works in the technical sense, but we want to get an idea of why we even care. Why do we have machines that give information to other machines? Why bother? And then we're going to talk about what kinds of things we do once we have that communication. But I want to start out with just talking about why do we have automation in general? So I want to start out with our own point of view. We probably have quite a few products around our house that were machine made, and some of those have replaceable parts. For instance, maybe you have a famous brand name water filter device. You keep the device, whatever housing it's in, but you're going to swap out filters after a while. Can you imagine if each one had to be handmade to fit the housing that you purchased? That would be enormously time-consuming and expensive. Or closer to home, imagine this. You're hungry. You decide you're in the mood for a cookie. So you get out the ingredients, you fire up the oven, and you make a cookie. A little while later, you say, that was good. So it starts again. You wouldn't think about doing that. In fact, where sometimes you'll see a recipe that says, this will make a dozen, this will make 2 dozen, you'll double that because you know that you're going to visit friends and take some or take them into work. It's mass production. When we save time or we save money by doing things the same way, doing them all together, we typically call those economies of scale. Well, to a degree, we won't get into business and politics, but to a degree, those economies of scale translate into savings for us. Because we've got manufacturers that can serve a wide market, then they are able to do more for us. The other thing that we can do, although it's not as common these days, but it is coming back in favor, is we can get repairs. Now, vehicles are still a good example of where we can get repairs because we've got interchangeable parts. And 2 of the pioneers of automation and manufacturing helped out with this. I just want to mention their names just to give you a little bit of history. The first, of course, is Henry Ford. Now, chronologically, he came after our other gentleman, but Henry Ford pioneered the use of the assembly line. He wasn't the only one, but he used it to make his product. He did kind of standardize some things, too, to make it easier. You might have heard his saying, you can have any color you want so long as it's black. Painting a vehicle is a complicated thing. And back then, without some of the sophisticated techniques that we have now, it was a little bit more complicated and a little bit more messy. So he simplified it down and produced a vehicle that a lot of people could afford. Now, before that, there was Eli Whitney, and you probably think of him in connection with his invention of the cotton gin, but he was one of the people that pushed for the manufacture of interchangeable parts. I've got some item that is broken and I can pull the part out that needs replacing, put another one in that's already made to fit. In his case, he was specifically interested in using interchangeable parts for firearms, and that idea has spread quite a bit. All right, so that's a little bit about the history, and hopefully I've sold you that even though sometimes we kind of look at big business and industry as undesirable, there are some things that they do for us and that they can achieve that really do help us out. When we come back, We'll talk a little bit about the different methods that machines use to signal each other and what kinds of information we can transfer back and forth by doing that. All right, I'd like to start out this section of the episode by using a small example here. So I want you to think about a small automated packaging cell that has 3 machines. It's got a conveyor system to move product, a robotic arm, and a labeling machine. The conveyor has a digital sensor to detect when a product has arrived at its pickup station. That digital input triggers a signal to the robot, and it could be over a digital output, which would be just a signal that's on or off. We're going to describe those in a minute, or a communication network. And then that is going to tell the robot, well, you've got the signal, go ahead and get the product. The robot uses the analog input from its gripper to make sure that it's exerting just the right amount of force and adjust it from an output that is also analog in nature, meaning it's continuous and can be adjusted. And once it's got the product onto the labeling station, it's then going to send a digital output signal to the labeler to say, go ahead and slap the label on this. Through the whole operation, the machines might also exchange status messages over some communication like Ethernet IP. That would allow the system controller to coordinate timing and handle exceptions in case, say, a fault comes up or there's some kind of a jam in, say, the label printer. Now, when we said controller, what we're referring to is typically something that might be referred to as a PLC, or programmable logic controller. And you could think of this almost as a traffic director that says, hey, I know that we've just got that box of product at the end of the conveyor because there's a sensor there. And when the box comes down the sensor, it either triggers something by pressing a switch or by blocking a beam of light that normally makes it to the sensor. So now the sensor shuts off. Whatever that signal is comes back to me. And now I'm programmed that when that signal says there's a box present, I'm supposed to send a signal out to the robot. The robot is programmed to say, when this signal gets to me, my response is to make certain motions, get to where the product is, and then signal my own grippers that they should close with a specific force that I can control by the level of the analog output I send out. And then we move back to our label machine. So the heart of this operation might be that programmable logic controller, although in real small operations, a lot of robots can actually control the other machines. So what were these types of signals that I was talking about? Well, the first one you heard about was the digital I/O. Now, they're what you think of when you hear digital. It's either on or off. And typically, you will be sending one signal down an individual wire, literally, and it's either on or off. That's all it can be. So we either have to go to a different type of output if we need more than that, or we're going to have to group them together to create binary numbers by combinations of inputs and outputs that are on and off in different sequences. But the point is, one machine is watching for that signal to appear or disappear, and it is programmed to respond to that. But that's digital. It's got that limited range. Now, let's say that we need to handle something like the force we just talked about on the grippers, where we might say, hey, for this box, it's got a certain weight to it. We need to grip it pretty tight. But for the next product, we don't need to do that the same. We may need to have an adjustable output along a scale, and that would be an analog output. And a lot of times in our industrial equipment, our digital outputs will be based on 24 volts. That is either there or is dropped to 0 as a signal. Analog will often be ranged in a range of minus 10 volts to 0 or 0 to 10 and anywhere in between. And what we can do is use the level of that voltage to signal something else we want. For example, If we're arc welding, we might need to ask that arc welder to deliver, say, 44 volts while we're welding. But we only have a 10 volt range of signal. So we use a process called scaling, where the weld controller knows that, say, 9.9 volts is a request for 44 volts of output from that weld controller, called scaling. And that allows us to do things like take a thermometer that will give us an analog output and read from a large scale of temperatures, but just translate it into that 10 volt range and still get the data correct. So that is analog I/O. And then there's communication based, and this is where we use protocols like Ethernet IP. And here we can take our signals, and rather than using the 24 volts or the 10 volt range, or in some cases we'll use current with communication based, we're sending data that is interpreted by special hardware at either the device end or the robot end or the programmable logic controller end, but it's the same kind of data that you would send over a computer network for other kinds of items. A good example of where we would use a very interesting kind of analog that I just want to include: when we go to paint a car, we may need some very specific airflows out to the end of the arm of the robot to control how that paint falls. Now, we can't have electrical signals way out at the end of the arm, because when we're painting a car, we're in a very volatile environment. So what we will do is, at the lower end of the robot, all sealed up so we don't have those volatile gases getting inside, we will translate our signal from whatever electrical, usually it's current, 4 to 20 milliamps, at a transducer that will then say, based on what you're sending me in analog, I know how much air pressure I should pass on to the end of arm. And we can reverse that too and read air pressure and translate it back into current, so that at all times our robot knows that it's sending exactly the right kind of air at the right amounts at the right spots to paint that car correctly. It's actually a very complicated process compared to what I'm making it sound, but I just wanted to give you kind of a good living example. Now, when we come back, I'm going to talk a little bit about situations where we go beyond just the robot or conveyor or other machine and PLC operation and work on a little bit larger scale, and some of the other advantages we get when we're doing that in manufacturing. All right, to wrap up, I want to talk about 3 manufacturing-related concepts that do involve communication, and just talk a touch about how they are also advantages of manufacturing. The first is JIT, or just in time. Well, I've got it here as automation, but it is also a concept in supply chain, and that's what I want to talk about the most. But an example I've got here in front of me says, imagine a JIT-driven assembly line where a robotic arm installs a part into a product only after a sensor confirms the product's arrival. There's no buffer of waiting parts. Instead, a part feeder delivers components just as the robot needs them. If the downstream machines slow down, upstream machine pauses too, keeping everything balanced and efficient. Now, this goes outside of the manufacturing cell or line or even plant as well. And what JIT also means in the supply chain is, if I'm the manufacturer and I know that I'm going to ramp up production, I'm going to be able to signal, but just before I need the parts. So my supplier has to be ready to get those parts manufactured and to me. If I'm slowing down, the same thing can happen in reverse. Communication of my inventory, billing, invoices, all of that can travel back and forth over something called electronic data interchange, EDI, where the suppliers can be aware of what the stock is at the customer and aware of their own and know how much more product to produce and when to deliver it. What this does for the OEMs means they don't have to keep warehouses to stock up parts. Good for them because less investment in real estate, literally. And then if anything happens that changes the market and they respond to that change, they are not stuck with an inventory of parts that they are not going to use anymore. Now, EDI relates to specifically the manufacturing process as far as stocks and invoicing, etc., mostly. But there is a new kid on the block, and you've heard of this player, IoT, Internet of Things. And that has a little bit different function, but related. The machines are still communicating, but in the Internet of Things, a lot of times what you're communicating are actual physical aspects of your operation. I'll give you an example. There is a large robot manufacturer that has a process called ZDT, zero downtime. Now, technically, although it's a very catchy name and it's a very good service, it's zero unplanned downtime is probably a better way to put it. And you can network your robots at your facility and then link your robot network up to the cloud that this robot manufacturer monitors. They will watch, you could say, the vital signs of your robot, and they will be able to let you know, hey, we see that you have something going on with such and such a robot at a certain joint on that robot. And if you listen to the episode on robots, you know at each joint there is a motor there. It goes into a reducer. Well, we might get a little bit of trouble at that reducer where the software at the manufacturer end says you shouldn't have to send that much current to make that motor move. Something's getting sticky there in that reducer. You need to plan on having a swap out of the motor and the reducer gear, whatever it is, before anything even goes down. You can get ahead of that. So that is zero downtime. That's just an example of how the Internet of Things works as an advantage. So those three items there, they're beyond the real basic communication we started out with, where we just had one machine trigger another and it was time for the other machine to move, etc. And you can see how it's a very much broader picture, and there's a place in it for everything from regular old electrical work all the way up to computer programming and network. Very wide field, and there's a place for a lot of people in it. All right, I hope that helps you get a good overview of how all these things work together and what advantages there are, even to the consumer public, when we work with automation in this way. Thanks for listening, and we will talk to you again soon. If you haven't subscribed yet, please do that. Please give us a rating on your favorite podcast platform and drop us a line as well. Thanks. That's all we have for today. This is Dean saying thanks for listening, and we hope to have you back with us next time on Teachers to Tech.